All right, welcome, ladies and gentlemen, to section 4.7. We are looking at the inverse trig functions. So we're going to look at arc sine, arc cosine, and arc tangent. Those are the only things that we really look at. You'll notice we skipped 4.6 only because it's not a super important section for us, and we're just going to look at 4.7, 4.8, and finish out chapter 4. All right, so let's go ahead and look at a few things. Let's first look at what does it mean to be an inverse function. So what do we know so far? We know things about the horizontal line test. If a function passes the horizontal line test, then it has an inverse. If there's more than one intersection for a horizontal line, there is no inverse. Inverses reflect, wrong way here. Inverses reflect over the line y equals x. And the reason this all comes down, we know the things about certain functions. If we were to ask ourselves, does y equals x squared have an inverse, we would look at its graph, and we would then do the horizontal line test. And those dots, those two intersections, mean that this function has no inverse. But here's the problem. Inverses mean something that undo each other, two functions that undo each other. And we know that the inverse of the square function is to take the square root. We just know that. When we solve equations, if we have something like 4 equals x squared, we know to take the square root of both sides because it undoes the square. So how are we supposed to get around this idea of not having inverse? Well, what we do is we say, well, we can limit the domain of the quadratic function to this right here. If we limited it to just the positive x values, we would end up getting all of the y values from both sides. All of the y values of the quadratic function occur on the right-hand side of the parabola. They just get repeated on the left side, so they're not necessarily required. And we know that because the square root of 4 is both plus and minus 2. So that actually, if it was 4 right here, it'd be plus 2 and minus 2. So the inverse, change my color of my pen here. The inverse, the square root function, is reflected across the line y equals x and looks like this. These two intersect point here at the 1, 1. So this is the square root of x, and this is x squared. They're reflected across the line y equals x, and that shows that we can have the inverse as long as we limit the domain where all of the range values are still occurring. So that goes to sine inverse. Now, I'm probably going to be calling it arc sine quite often. Both are used synonymously. They're the same exact thing, sine inverse and arc sine. They're exactly the same thing. Only reason I put the sine to the -1 here is, 1, it's a little easier to write, and 2, this is the button that's on your calculator when we get to that point of plugging it in our calculator. Quite honestly, I usually see this in the more real-world applications of the inverse functions. They use the word arc sine a lot more, I believe, in the engineering level and that sort of stuff. So let's look at one period of sine x. If we looked at one period of the sine of x function, we could look at that function and say, well, that does not have an inverse. It does not pass the horizontal line test. So then, just like with the quadratic function, we need to limit the domain. If we limit the domain to get all of the full range, then we can say that it has an inverse. And what we're going to do is, instead of looking at going from up and down, because that doesn't do it. We got to look at something that's going to get all of the values from -1 to +1. And we could start over here and go from pi halves to 3 pi halves. But what we like to do is we like to center the function on the y-axis. So if we went backwards a little bit, this now showing 2 full periods of the sine function. And if we went from negative pi halves to positive pi halves, that will get the entire range of sine, and we would eliminate the rest of the function. So what we're going to look at, if I erase this and try again here, we're going to look at the sine function that goes from negative pi halves to positive pi halves and does this. This contains the entire range of sine, and this function now has an inverse because it passes the horizontal line test. So this is just what I was just saying there. With this new limited function, we can swap the x and y axis and graph the reflection of sine inverse, or of sine, where the sine inverse, if we swap the x and y axis, this is going to be pi halves. This is going to be negative pi halves. This is going to be 1, and this is going to be -1. Because that's the whole idea of swapping x and y when we did the inverses way back when. And at negative pi halves, it's -1. And at positive pi halves, it's +1. And it's going to go something like this. This is the graph of sine inverse of x. A couple things that we're going to need to know if we reflect there. So I was just saying here, the domain for this sine inverse function is -1 to 1. And the range is from negative pi halves to pi halves. What I'm going to point out, because this comes in handy later on, is that from negative pi halves to positive pi halves is quadrants 1 and 4 on your unit circle. That's very important for us because our answers to any sine inverse problem can only come from quadrants 1 and 4. If our answer comes from quadrants 2 or 3, they're wrong, and you must find the reference angle in quadrants 1 and 4, and you'll see what I mean in a little bit. So that's arc sine. Let's go ahead and take a look at arc cosine. So again, if we look at the full period of cosine, cosine starts like this and comes up like that. We also need to limit this function the same as we did with sine, only in this case we're going to use different values because it's a different function. In this particular case, we are going to go from 0 to pi, pi being right here. Oops, not pi halves. Pi being right here, so therefore we get all of the range values for cosine. So if we were to look at the limited domain for cosine, it's going to go like this, from 0 to pi. And what we're going to do is we're going to regraph for the cosine inverse. Again, swap the x and y and reflect the graph. If we swapped the x and y direction, oops, let's get rid of that there. Let's try that again. I don't need anything below the x-axis. My x-axis goes from -1 to 1, and my y-axis goes from 0 to pi. We swap the directions there. And at -1, it's at pi. And at 0, or at 1, it's 0. And in here at pi halves is where it crosses the x-axis. And I always have to think about this because I always draw these a little bit weird. I always end up drawing them wrong. It's got to go this way. I'm pretty sure. All right. So this is the graph of cosine inverse of x, or arc cosine. So again, I'm going to give you guys the same kind of idea here. The domain for cosine inverse is -1 to 1. Remember, that means I can only plug in numbers between -1 and 1. I can't plug any numbers outside of -1 to 1. So if I try to do cosine inverse of 2, that doesn't exist. There's no number 2 in the domain of cosine. The range is from 0 to pi, and again, I'm going to note that that is from quadrants 1 and 2. All right, last but not least, we're going to look at tangent. These are the only 3 that we look at here. If we were to look at tangent itself, here's negative pi halves and positive pi halves. And tangent ends up looking like this. That's one full period of tangent, and you'll notice that that actually passes the horizontal line test, as long as we don't draw any other parts of the function. Remember, this thing repeats the same piece over and over and over and over again. So we can limit on just the original domain, or on the original first period that we graph from the last couple weeks. So if we were to graph one period, you notice here that we can do it without limiting the domain more than just what's given there. We don't have to find the pieces that we want. We're doing the same thing as we did before. We're going to swap the x-axes, swap the x and y-axes, except for now, my y-axis has my asymptotes because those vertical asymptotes become horizontal. And my x-axis does this -1 to 1 thing. It goes through the origin still. And we are here and here. And we do our best to draw the curve thusly. And if you think about it, remember this looked like a cubic function-ish. And this kind of looks like a cube root function. And they should kind of look the same. All right. I did not draw that very well, but I think you get the idea. It goes through the dot and then curves on the asymptote, and this goes through the dot and curves through the asymptote. So the domain here, if you look at this particular function, the arctangent function, the domain is all real numbers. Whereas now the range is from negative pi halves to pi halves, and likewise with sine, that's from quadrants 1 and 4. So let's kind of look at what we're going to be doing with these 3 functions. One thing we're going to be doing is solving equations, but that comes in the next lesson. But right now, we're going to be just looking at just solving simple problems. Back when we said x squared equals 4, what's x? We figured out that that's 2 and 2, or 2 and -2. Here, we're going to look at it a little bit differently. We're going to say sine inverse of 1/2 is equal to y. Well, what this means, what's something we can say with this, is that the sine of what y value, or what angle, is equal to 1/2. Well, there is a spot in your circle where the sine of an angle is equal to 1/2. And if you look, it has to be from quadrants 1 or 4, as defined in the 2 slides ago, or 3 slides ago, when we talked about sine inverse. So the sine of y, what angle has the sine of that angle equals to 1/2? And we know that that's the 30-degree angle, because we know the sine of 30 degrees is half, or in other words, pi over 6. Likewise, We can say cosine inverse. We can say tangent inverse. Whatever these problems come down to, and it really comes down to knowing your unit circle. Here I'm looking for cosine inverse of root 2 over 2 is equal to y. Well, this has to come from either quadrants 1 or 2, as defined in cosine inverse. And we're again going to think cosine of what angle is equal to root 2 over 2. So we can go to our unit circle. We would find that that happens at the 45-degree angle. And we are going to look at quadrant 1, not 2, because that's negative root 2 over 2. Oops, not pi 6, pi 4. Sorry about that. All right, but not everything's going to be quite that easy. What if I was to ask you something like this? The sine inverse of pi halves. Well, you can't just go to sine of pi halves because that's not what this is asking. This is asking I should have said equals y here. The sine of what angle y is equal to pi halves? Well, that's not a correct question in just using the unit circle. However, you might be able to use your calculator. The problem here, though, is pi divided by 2 is equal to 1.57. And if you recall, the domain of sine inverse is from -1 to 1, and therefore this does not exist. There is no answer to this question. There's a couple problems here. Every once in a while you got to use your calculator on. Do not use every problem with your calculator. You need to be able to do this stuff in your head. Some of it, like the first two problems here, you should be able to do sine inverse and cosine inverse of these two values in your head, thinking sine of what angle equals a half. In these two cases, you're going to plug in the calculator because there's nothing on your unit circle that gives you 0.35. And so you'll plug this in a calculator. I'm not going to do this for you. I think you can do it. And here's the big thing. If you're in radian mode, your answer is going to be a radian measure. If you're in degree mode, then your answer is going to be a degree measure. So make a note of that. You could have the different answer than your neighbor depending on whether or not you're in degree or radian mode. Just pay attention to the question. If the question says, find your answer in radians, or if it says something like this, where 0 is less than or equal to theta is less than 2 pi, that means your answer should be in radians. This means your answer needs to be in degrees. All right, the different statements. Also note here, arc cosine of 2 does not exist. You should not have to plug that into your calculator. You should just look at that and automatically know it doesn't exist because the domain of arc cosine is also -1 to 1. All right, that's one of the things we're going to be doing with this to go along with solving equations. And let's look at something else. Compositions happen all the time with inverses. This works in this particular statement where I say sine of sine inverse of x is equal to x as long as it's defined. If you tried to do something like this, the sine of sine inverse of 2 equals to 2, that would be bad. Because sine inverse of 2 does not exist. So that's not defined, so that can't be true. So as long as x, in the first case, is between -1 and 1, and cosine -1 and 1, and tangent anything really, as long as that's defined, you can do that. The same thing kind of goes in the other direction. If you try to do sine inverse of sine of x, it's only true when x is part of the restricted domain of sine x. or sine x, cosine x, tangent x. That being said, it has to be something along the lines of this. If x is outside your domain, remember the domain for sine, the restricted domain for sine x is negative pi halves to pi halves. So I can't do something like this. I can't say this right here. I'll just do this example here. Sine inverse of the sine of 5 pi 6 does not equal 5 pi 6 because 5 pi 6 is not in the restricted domain. If you think of your unit circle, you're only allowed quadrants 1 and 4 for sine and sine inverse. However, 5 pi 6 is over here. And if you have to do this problem, which it's still a doable problem, but you have to find the answer or the angle that coincides to quadrants 1 or 4. And if you think about this, the reference angle here is 30 degrees, or 1 pi 6. You know that the sine of 150 is a positive number, so we're looking for the sine of a positive number here. We can say that the sine of 5 pi 6, what we're doing here is rewriting this. We know that the sine of 5 pi 6 is the same thing as the sine of 1 pi 6, so we can replace it and now make a true statement in the composition. So the sine inverse of this thing is equal to pi 6. So that means this thing here, the sine inverse of the sine of 5 pi 6 is equal to pi 6. All right. I know I've talked your ear off so far, but I have one more thing to go along with compositions. Things like this. They don't follow those last rules because they're not the same function. So we have things like cosine of sine inverse of 1/2. But here's what we're going to do. We're going to look at the inside piece. Whenever we do the cosine of something, it has to be the cosine of an angle. So we're going to let this thing on the inside, the sine inverse thing, we're going to let that be theta. And what that means is that means that the sine of theta is equal to 1/2. Well, we can solve that. That means that sine is 30 degrees if we just kept with the degree measure. Which means that the sine inverse of 1/2 is 30, so we can replace that with 30, and that means the cosine of 30 is root 3 over 2. But what if? What if it didn't give you a number? What if it gave you an x? Well, that changes things a little bit, but the process is still the same. In the same fashion that we did in the beginning, where we said sine inverse of half is equal to theta, we can say cosine of inverse of x is equal to theta, which then tells me that x is equal to the cosine of theta. Well, it doesn't really look like it's helping us at all, but what we can do is we can go back to what we know about right triangles and trigonometry. If this is my theta, it says the cosine of theta is equal to x. Well, x is the same thing as x over 1, and we know cosine is adjacent over hypotenuse. By using the quadratic form, or not quadratic, Pythagorean theorem, we can find that this side is equal to 1 minus x squared under the radical, which then means we can find the sine of theta. Oops, sorry about that. We can then find the sine of theta by just looking at the triangle that's been given. If I was to redraw this triangle here for us. x1 theta square root of 1 squared minus x squared. And we can say that the sine of theta is equal to the square root of 1 minus x squared over 1, but that's not necessary. So this would be the answer to this question. All right, you notice that that's actually the last piece that we're going to do. I hope you learned a lot today. There's a lot in this particular lesson. Come ready tomorrow, and I'll see you guys tomorrow.